Let's continue from the last lecture. So, we were looking at discrete time sinusoids, and the difference that we saw was e to the j omega naught plus 2 pi times n was the same as e to the j omega naught n. Therefore, omega 1, if it is omega naught plus 2 pi, which is greater than omega naught, yields exactly the same signal. Even though the frequency is different, as far as the signal is concerned, you get the identical signal back. And we saw that omega naught equal to 0 and omega naught equal to 2 pi both yield the DC sequence. But as omega naught increases, you expect the rapidity of the oscillations to increase, but looks like it is going to slow down at some point and come back to the DC sequence, and this is easily seen in this example. So, this is from Oppenheim's book. So, we are looking at the cosine signal here. So, this is omega naught being 0, and then the frequency is increasing as we go along. This is cos pi n by 8, this is cos pi n by 4, and so on, and this is cos pi n by 2, and this is cos pi n. Cos pi n is minus 1 to the n. So, this is plus 1, minus 1, plus 1, minus 1, and so on. And now, omega naught keeps on increasing beyond pi, and this is cos 3 pi n by 2, and this is further increase in omega naught numerically. So, this is cos 7 pi n by 4, this is 16 pi n by 8, and clearly you see beyond pi the sequence, the rapidity of the oscillations slows down, and when you hit 2 pi you are back to where you started off, namely omega naught equal to 0. So, this is a simple example that illustrates the fact that as you increase omega naught, the rapidity does indeed increase, but unlike in the continuous time case, looks like it reaches highest frequency of oscillation, and then the signal starts to slow down and then comes back to the DC sequence when omega naught equals 2 pi. So, this can be kind of captured in this. So, this is omega naught. Omega naught belongs to the interval minus infinity to plus infinity. However, as far as the signal is concerned, because omega naught and omega naught plus 2 pi are the same frequency in terms of the signal that is being produced, you can replace omega naught by omega naught mod 2 pi, and if you plot omega naught mod 2 pi, this is what you get. So, this is omega naught mod 2 pi, and this is the behavior of the modulus function with respect to 2 pi. And moment you take mod, it is clear that you need to consider values of omega naught only between 0 and 2 pi, because any value outside this interval can be mapped to within this range. The other way of looking at this is, rather than restricting it from 0 to 2 pi, you can go between minus pi and pi. So, the other graph that shows this is this. All right. So, this point is pi, this also value is pi, this value is minus pi. As omega naught becomes greater than pi, you wrap it and then it maps a point here, maps to a point here. Let me call this as omega 1, and omega 1 belongs to the interval minus pi to pi. And looking at omega in this range between minus pi and pi, get a feel for why the signal frequency slows down. If you now plot mod omega 1, then of course from 0 to pi it is the same curve, nothing changes because it is positive. But if you look at the value of omega 1 beyond pi, then if you look at the modulus, then the curve looks like this. So this also gives you a feel as to why the frequency decreases. So from 0 to pi, the rapidity of the oscillations increases. At pi, you reach the highest frequency, and then beyond pi, the frequency actually decreases, as you can see from the modulus function, that is taking the absolute value of omega 1. So because omega is going to be restricted in the interval 0 to 2 pi, it is good to plot that on a circle rather than on a line. So this is omega naught equal to 0. Here omega naught is increasing. The oscillations are also increasing. So this happens till omega naught reaches pi. So this is omega naught equal to pi. Pi is also the same point as minus pi. Now beyond pi, omega naught is still increasing. However, the rapidity of the oscillations decreases, and it keeps on decreasing till you hit 2 pi, when you now reach the DC sequence. So this is another way of looking at how things are as omega naught changes from the interval 0 to 2 pi. And typically we will be focusing on omega naught in the range minus pi to pi. So this is one distinct difference between discrete time and continuous time. Recall that in continuous time, e to the j omega naught t and e to the j omega naught plus 2 pi. These two are two distinct exponentials, they are not the same. So this is the first difference. The other difference, again this is a review for you, is e to the j omega naught n always periodic. Remember, e to the j omega naught t is always periodic with period t equal to 2 pi by mod omega naught. Now let us consider the discrete time sequence. We want x of n equal to e to the j omega naught n. Under what conditions is x of n plus cap n the same as x of n? All you need to do is, you need to see under what conditions e to the j omega naught n plus cap n equals e to the j omega naught n. So clearly you require e to the j omega naught n. So this should be e to the j 2 pi k, right. Therefore you require omega naught n must be the same as 2 pi k, or omega naught by 2 pi must be the same as k by n. And omega naught by 2 pi, the commonly used notation is to denote this as little f naught. So, if and only if f naught equals k by n, so this means this is a rational number. Only in these conditions is x of n equal to e to the j omega naught n periodic with period cap n. Now, the further inferences can be drawn from this development. Recall that omega naught is really omega naught mod 2 pi, which means that f naught, which is nothing but omega naught by 2 pi, is really f naught mod what? Mod 1, right? Because if omega naught is mod 2 pi, since f naught is omega naught by 2 pi, a little f naught has to be in the range 0 to 1 or between minus half to plus half. So, this means that f naught, which is f naught mod 1, remember f naught for the exponential to be periodic has to be of the form k by n, and k takes on the values 0, plus or minus 1, plus or minus 2 and so on. But because f naught is the same as f naught mod 1, then you need to restrict yourself as far as k is concerned to the range what is the value of k that you need to consider? Minus n by 2 to plus n by 2, that opens up what, n odd, n even and so on. An easier way of stating that would be 0 to n minus 1, right. So, this must be in the range 0 to n minus 1, because if k were equal to n, then that is the same as k taking the value 0. So, this implies that k is really k mod n, all right. Therefore, for example, if you take n equal to 4, remember we are now looking at complex exponentials that are periodic. So, if you consider n equal to 4, I am now plotting the various frequencies that are possible, assuming that the periodicity is 4, all right. So, which means k needs to take the value 0, 1, 2 and 3. Therefore, if k takes on the value 0, you will have omega naught here. So, this is k equal to 0 and this is k equal to 1, 2 and 3, okay. Therefore, you have e to the j omega naught n little n. Now, this is in this particular case we have cap n to be 4. Therefore, let us look at all the possibilities. So, this can be written as e to the j 2 pi by n k times little n. So, these are the various complex exponentials that are possible for period cap n, and in this particular case we are going to let n equal to 4. Therefore, we have e to the j 2 pi by 4, you have k equal to 0 and then n. So, this gives you the first complex exponential. Then e to the j 2 pi by 4, k is 1 times n, 2 times n, and then e to the j 2 pi by 4, 3 times n. So, these are the 4 distinct exponentials that are possible here. Note that when k equal to n by 2, when n is even, then the frequency corresponding to that particular value of k is when k is n by 2, remember we are looking at the set of complex exponentials e to the j 2 pi k by cap n times little n. So, this let me call this as xk of n, and k itself will take on the value 0, 1, 2 up to n minus 1. Here I am considering the case as a specific example when cap n is 4, all right. So, I get these 4 distinct exponentials. Whatever distinct means, we will make it more precise. So, when cap n is even, when k equals n by 2, what will be the signal that is produced? So, that is exactly this particular case, right. So, you get e to the j pi n, right, because in this if you put k equal to n by 2 where cap n is even, you will get e to the j pi n, all right. So, remember this also corresponds to the highest frequency pi, which is also the same as minus pi. Because k is the same as k mod n, the index k equal to 3 also corresponds to the index k equal to, what is one other k that you can immediately think of in the place of 3? Seven, okay. Minus 1. 7 also is correct, minus 1 also is the right answer. So, this also corresponds to k equal to minus 1, this corresponds to k equal to minus 2, and this corresponds to k equal to minus 3, all right. And these are what are called a set of harmonic sinusoids. These sinusoids are a set of sinusoids that are harmonically related, and when cap n is even, when k hits n by 2, you will reach the highest frequency, namely pi. On the other hand, suppose n equals 3, then xk of n is e to the j 2 pi k by 3 times little n, and here k takes on the value 0, 1, 2, and if you plot these points on the circle, k equal to 0 will correspond to this frequency, k equal to 1 and k equal to 2. So, these are the 3 values of k, and these are the values of k times omega naught that I have plotted on the circle here. Notice that in this particular case, you do not hit the highest value of pi, all right. So, remember, when n is odd, what is the closest integer that gets you to pi? What value of k gets you a frequency that is closest to pi? N minus 1 by 2. So, k equal to n minus 1 by 2 produces a signal whose frequency is closest to pi. The other value of k that will also produce something that is closest to pi will be n plus 1 by 2, and what will be the actual frequency? So, 2 pi by n times k, k is n minus 1 by 2, and here you have 2 pi by n, n plus 1 by 2, all right. So, the actual frequencies are pi times 1 minus 1 by n and pi times 1 plus 1 by n. So, these are the 2 sinusoids whose frequencies are closest to pi. You do not actually hit the pi frequency because n is odd. Therefore, if in general if x of n equals x of n plus cap n, then we produce sinusoids of the form e to the j 2 pi by cap n times k times n, and then k itself goes from 0, 1 up to n minus 1, and then we have each of these sinusoids is periodic with period cap n, and we have n distinct sinusoids. Now, let us kind of understand this a little more. So, we need to restrict ourselves only in the range 0 to 2 pi. So, we start off with omega naught equal to 0, and then we keep on increasing omega naught. For every value of omega naught, you produce a sinusoid, and omega naught varies continuously from 0 to 2 pi. So, as omega naught varies continuously from 0 to 2 pi, you produce uncountably infinite different sinusoids. In this range, among these uncountably infinite number of sinusoids, there is one finite set of sinusoids, namely e to the j 2 pi k by cap n times little n. Among this uncountably infinite set of sinusoids, this set of sinusoids is the only one that is periodic with period cap n, all right. Whereas, in the continuous time case, you have e to the j k omega naught t, this is the counterpart there, and then you let k in the range minus infinity to plus infinity, okay. Okay, so these are harmonic sinusoids in the continuous time case. You have a countably infinite set and all of them are periodic. The general case is you have e to the j omega naught t, and now you can let omega naught in the range minus infinity to plus infinity. Omega naught varies continuously in this range. Again you get an uncountably infinite number of sinusoids. Here every single sinusoid is periodic. In the continuous time case, every single sinusoid is periodic, alright. Whereas in the discrete time case, as you let omega naught vary from 0 to 2 pi continuously, you get an uncountably infinite number of sinusoids, but among them only this finite set of sinusoids, namely cap n in number, are periodic. So this kind of reinforces the similarities and differences. We made the statement we have n distinct sinusoids. So this is a rather descriptive term. We will make this term more precise and see what distinct really means.